This question is about time of flight mass spectrometry. Compound X is dissolved in a polar volatile solvent and ionized by electrospray ionization. That's quite important because that is where our molecule, so we're calling it X, not M, X picks up a proton from the solvent and becomes XH plus as it travels through the spectrometer. Each ion is accelerated to have a kinetic energy of 1.36 times 10 to the minus 16. It's given us the equation for calculating kinetic energy. It's half the mass in kilograms times the velocity in meters per second squared. The time of flight along this is a distance of a flight tube, and this is a time. And then it says determine the mass in grams of 1 mole of X. So the first thing that we need to do is work out the velocity by doing distance divided by time. So distance in meters divided by time in seconds. So I want to type that on our calculator. So 0.75 over 2.48 times 10 to the minus 5. And we're getting quite a large number because they travel quite fast in the mass spectrometer. And you can keep that on your calculator screen or round it up. If we're going to find the mass, at the moment we can only rearrange kinetic energy to find the mass in kilograms of one atom, not the mass of a mole. But we rearrange the expression, we'll get 2 times the kinetic energy divided by the velocity squared. So we can put our numbers in, 2 times the kinetic energy that they've given us, divided by our velocity that we've just calculated. You could keep that on your calculator screen and use it. So if you were to press, if that's still on your calculator screen now, if you were to press the fraction button and do 2 brackets 1.36 times 10 to the minus 16 and close your brackets, go down to the bottom line and press answer and then press squared, everything will go in your calculator without you having to retype. That is giving me 2.974 times 10 to the minus 25 kilograms for 1 ion. So I need to get it in grams for 1 mole. So the mass in grams is, we're going to times by 1,000. And so that gives us, so you just can press answer times by 1,000 on your calculator, 2.974 times 10 to the minus 22 grams. That's still of 1 atom. So we're then going to times by Avogadro's to find out the mass of a mole. Again, it's still on your calculator screen, so keep just adding. 179.1 is what my calculator is coming out with. And you will possibly get ever so slightly different answers depending on rounding errors. Okay, but remember that this is the mass of what came out of the mass spectrometer. So MH plus equals 179.1. So M equals 179.1 minus the 1 for the hydrogen, 178.1. I'm just going to round it to 3 significant figures and write 178. A mixture of gases is analysed using time of flight mass spectrometer. The mixture contains argon, carbon dioxide. So we've got a mixture and we've got argon, CO2, nitrogen and oxygen. State the meaning of the term electron impact ionisation. So we're basically being asked to explain what's happening in electron impact. So high energy electrons from an electron gun knock off an electron from our sample. So when we use this, we would go like our sample, and this time it would become X plus gas plus an E minus. Identify the ion formed from this mixture that reaches the detector last. would be the slowest, which equals the heaviest. So if we look at them, we need a periodic table, and we're going to have a look at each one. So argon is 39.9, oxygen is 216s at 32, nitrogen is 214s at 28, carbon dioxide is a 12 and 32, so 44. And so we would expect the heaviest is carbon dioxide. But remember, we're doing the iron, and they're all being ionized by electron impact, so they're just becoming positively charged ions. They're not gaining a proton like electrospray. And justify why this would meet the detector last. So it has the highest mass, so it travels the slowest. State how the ions are detected and how the abundance of each ion is measured in a TOF spectrometer. So when they hit the detector, each ion gains an electron, and this generates a current at the detector. How is abundance measured? The size of the current generated is proportional to abundance.